So we're going to go through the answers for the P1 exam questions. So remember, question 1 is foundation paper only, 2 and 3 are foundation and higher, and then 4 is higher paper only. I've got a highlighter so I can highlight the important data, a pen, and I've also got a calculator so I can do the calculations. So the diagram below shows a cyclist riding along a flat road. Complete the sentence. Choose answers from the box. So as the cyclist accelerates, the chemical energy stored in the cyclist's body decreases and the kinetic energy of the cyclist increases. So the mass of the cyclist is 80 kilograms. The speed of the cyclist is 12 meters per second. Calculate the kinetic energy. Use the equation. Kinetic energy equals 0.5 times mass times speed squared. So this is an equation that you are expected to be able to recall as well, but on the foundation paper, sometimes they will give you an equation because then they're testing whether or not you can use the equation. So we're going to substitute in. So we're being asked about the energy. So we're going to have 0.5 times the mass, which is 80 because it says it here, times the speed squared, so 12 squared. If I do that on my calculator, I have 5,760 joules. When the cyclist uses the brakes, the bike slows down. This causes the temperature of the brake pads to increase by 50 degrees Celsius. The mass of the brake pads is 0.040 kilograms. The specific heat capacity of the material of the brake pads is 480 joules per kilogram degree Celsius. Calculate the change in thermal energy of the brake pads. Use the equation, change in thermal energy equals mass times specific heat capacity times temperature change. Again, so this is actually from P2, which you might not have revised yet, but you should still be able to do it using the equation that's given. So the mass here is 0.040 because we've highlighted it. 0.040. The specific heat capacity is 480. And the temperature change is 50 degrees. So again, putting this into the calculator. And we get 960 joules. How is the internal energy of the particles in the brake pads affected by the increase in temperature? So remember that internal energy is the sum of the kinetic and potential energies of the particles in the substance. So therefore, if the temperature is increased, then the internal energy is also going to increase. So this diagram shows a tennis ball being thrown vertically in the air. So we've got positions A, B, and C, and somebody's hand. At position C, the ball has just left the tennis player's hand at a speed of 5.0 meters per second. The tennis ball has a mass of 0.058 kilograms. Write down the equation that links kinetic energy, mass, and speed. So we know that kinetic energy is equal to 1/2 times mass times velocity squared. You can give it in symbol form or you can write out the letters, but for the purposes of trying to get through this quickly, we'll give it in its symbols. Calculate the kinetic energy of the tennis ball at position C. So we're going to use this equation. Ordinarily, I would encourage you to write out the equation before substituting in the values, but because we've got it written here, just try and make sure that you're writing in the values directly below what you've got. So kinetic energy is equal to 0.5 times mass, which is 0.058, times v squared, so v being speed, 5.0 squared. So make sure that it's the 5 that you're squaring. So 0.5 times 0.058 times 5 squared. So kinetic energy is 0.725 joules. So at position A, the tennis ball is at its maximum height. What is the gravitational potential energy of the tennis ball at position A? Ignore air resistance. So it's only 1 mark, so you're not likely to have to do a proper calculation. What they're testing is whether or not you remember about conservation of energy. If they throw the ball from here, it's got kinetic energy here, and that energy as it goes up is going to transfer to gravitational potential energy. So at the bottom it's going to have its maximum kinetic energy, its lowest gravitational potential energy. By the time it gets to the top, it's going to have the highest gravitational potential energy, the lowest kinetic energy, because those will have transferred into each other. So it will go from the kinetic store at the bottom to the gravitational store at the top. So if it had 0.275 joules in the kinetic store at the bottom, then by the time it gets to the top, it's going to have the same, so 0.725 joules when it gets to the top at maximum. So at position B, the tennis ball has 0.38 joules of gravitational potential energy. Write down the equation that links gravitational field strength, gravitational potential energy, height and mass. So gravitational potential energy is equal to mass times gravitational field strength times height. Calculate the height of the tennis ball above the tennis player's hand when at position B. Gravitational field strength is 9.8 newtons per kilogram. Okay, this time around we are going to write out the equation again. So we have energy is equal to mass times gravitational field strength times height. Then we're going to substitute in our values. So I know that the energy is 0.38 because it tells me up here. I know that the mass of the tennis ball is over on this page, so 0.058. G is 9.8 because it tells me here. And I'm trying to find out H. So I would always suggest that you simplify wherever you can first. So we're going to keep 0.38 on this side, and we're just going to simplify this side first so that we have one number. 0.058 multiplied by 9.8 gives me 0.5684 times H. So I want to get H by itself, and at the moment I have H times 0.5684, so I have to do the opposite of this, which is divided by 0.5684. If I do that to this side, I also have to do it to the other side as well. So I'm going to do 0.38 divided by 0.5684 is going to be equal to H. So if I do that on my calculator, 0.38 divided by 0.5684, then we get 0.66854. So this is going to round, so we'll round that to 0.67 meters. A student finds some information about energy saving light bulbs. A 30-watt light bulb uses 600 joules of electrical energy in a certain period of time. In that time, it produces 450 joules of light energy. The rest of the energy is wasted. Calculate the energy wasted by the light bulb in this time. Well, if it has 600 going in and 400, so we could draw a diagram with this. So there's 600 going in, and then coming out, you've got 450 is light. So then the other, remaining amount is wasted. So we need to find the difference between 600 and 450. So 150 joules. What happens to the energy wasted by the light bulb? It is transferred to the surroundings by heating. Calculate the efficiency of this light bulb. So efficiency is an equation you need to learn, is the useful output divided by the total input. And this could be power, it also could be energy. It's just a ratio of the useful to the total. So our useful output energy is 450. Our total input is 600. So if we do 450 divided by 600, then we have 0.75. So you could give this as 0.75. You could also multiply it by 100 to say that it's 75% efficient. If it doesn't specify giving it as a decimal or as a percentage, you could do either. So calculate the period of time in seconds during which the 600 joules is provided to the 30 watt light bulb. So you're going to need to recall that power is the rate of transfer of energy, so it's energy over time. So we're going to substitute in our values. So power is 30, our energy is 600 over time. So we need to work out what T is. So either you could know the shortcut of rearranging for this, which is just to swap these two over, or you could think about it step by step with algebra, in that I would have to multiply this side by T, so have 30T, and then divide by 30. So let's do the quick way. 600 divided by 30 is 20. Okay, a company that makes light bulbs provides information about some of their products. The table shows some of this information. So we've got a filament bulb, power, lifetime hours, cost of bulb, LED, same information. Suggest why it is important to confirm this information independently. Basically, this is just to avoid bias, because if it's a company that makes light bulbs, then they might be trying to get you to buy the kind of light bulbs that they're selling. Okay, so we're probably going to need to keep this table close by, so we could do both. So a homeowner is thinking of replacing his filament bulbs with LED bulbs. A 12 watt LED bulb gives the same light output as a 60 watt filament bulb. Suggest reasons why the homeowner is likely to choose LED bulbs. Use the information given in the table. So it's a 2-mark question, so you're probably going to want to say 2 things. So first of all, lifetime in hours is much, much longer. So it's the fact, so therefore they're going to last longer, and they also use less power. So use less power, and they last longer. To use the information as well, what you could do is work out how many filament bulbs you would need to match the LEDs. So if you've got 50,000 hours divided by 1,250, then you would have 40 filament lamps for every LED bulb. And if you could actually find out how much that would cost, so times 2, because they're £2 each. So therefore, one LED is £16, but you would need 40 lamps to equal that number of lifetime hours, and that would be £80 for your filament lamp. So although it costs more in the first place to buy LEDs, in the long term they would pay for themselves. I suppose the other thing you could do is link it to power, and you could think about the fact that filament lamps, well, so it will cost more for your energy, so you could work out how many times more. 5 times more will cost 5 times more in energy. So state one factor other than efficiency that is important when considering the choice of a bulb for lighting in the home. You might want the temperature. You might not want lamps that get hot. You could say the colour. Some lights are very yellow, some lights are very white, and that might be something that you want to kind of think about. And availability. You get some bulbs. Availability of the bulb. So you get some bulbs that are a bit of a weird shape or size, which then makes it very difficult to like source them again. So that would be something. Lots of different things to think about. Okay, so the figure below shows a student before and after a bungee jump. The bungee cord has an unstretched length of 20.0 meters. So at the lowest point it's 55. The mass of the student is 50 kilograms. The gravitational field strength is 9.8 newtons per kilogram. Write down the equation that links gravitational field strength, gravitational potential energy. So we've already done this in this, but let's just write it again. EP equals mgh. So calculate the change in gravitational potential energy from the position where the student jumps to the point 20 meters below. So we're being asked for the gravitational potential energy. Their mass is 50. Gravitational field strength is 9.8 because it tells us here. And the height change is 20 meters. So 9,800 joules. Okay, so 80% of this change of gravitational potential energy is changed to their kinetic store. So how much has the kinetic store increased after falling 20 meters? So we had 9,800 joules. So we want to find 80%, sorry, not 90%. So we'll do 9,800 multiplied by 0.8 to give us 7,840, which is 80% of 9,800. Calculate the speed of the student after falling 20 meters. Give your answer to two significant figures. So we now have the kinetic energy. Usually the questions, they follow on from each other. So if it's just asked you about kinetic energy and then it's asking about speed, it wants you to use the kinetic energy equation. So energy is equal to mass at half times mass times velocity squared, or speed squared. So we need to substitute in and then rearrange this equation. So the energy is 7,840 is equal to 0.5 times their mass, which is 50, times v squared. So again, I would simplify this side. So I'd have 7,840 is equal to 25, because that's half of 50, 0.5 times 50. So we'd have 25 v squared. I want v by itself. Now we'll ignore the squared bit to start off with. I've got 25 v squared, which means that I need to divide by 25. So 7,840 divided by 25 will give me v squared. 7,840 divided by 25, which gives me 313.6. That's v squared though, and I don't want v squared, I want v. So I need to square root 313.6 to get v, which gives me 17.7087. So it's asked me to give it to two significant figures, so 1, 2, but after that second significant figure is a 0.7, so therefore that's going to round up, so therefore 18 meters per second. At the lowest point in the jump, the energy stored by the stretched bungee cord is 24.5 kilojoules. The bungee cord behaves like a spring. Calculate the spring constant of the bungee cord. Use the correct equation from the physics equation sheet. So it's given me energy, so therefore I want the elastic potential energy equation, which I can tell you is a half times the spring constant times the extension squared. So we know that the energy is 24.5 kilojoules, so that's 24.5 thousand joules, so we could write it as 10 to the 3 joules. 24.5 times 10 to the 3 is equal to 0.5 times k times, and then the extension, we need to look back at our diagram. So remember that the extension is how much it is stretched past its like unstretched length. It tells us the unstretched length is 20 metres, its lowest point, so the maximum it gets to is 55.0, so it's the difference is our extension, so 55.0 minus 20.0 is 35. So 35 squared, and remember again it's the 35 that you are squaring. So as we've done before, let's simplify this side. So I've got 24.5 times 10 to the 3 is equal to, and then I need to do 35 squared multiplied by 0.5. So I've got 612.5k. I want k by itself, so I need to divide by 612.5. If I do that to this side, I have to do it to this side as well. 24.5 times 10 to the 3 over 612.5 is equal to k. So remember when you're doing standard form to use this button at the bottom here, 24.5 times 10, it says times 10 to the x, so it brings up a little times 10, and then you just want to put 3 in after that, divided by 612.5, and that gives me a spring constant of 40 newtons per metre.